Hello. This is the Stayin Alive CPR training application by Andrew Lewis, Isaiah Haley, and Olayemi Ibrahim. I am Olayemi Ibrahim, and I will be starting off this presentation. So, what is the objective of our project? Essentially, the objective of our project is to develop a CPR training application which will give feedback on a trainee's technique based on output from a specially designed sensor placed within a mannequin, compiling information in easy to read graphs, gauges, and stats. The goal of this project is to allow for a way for new students of CPR training to gauge their work and make improvements on their CPR techniques. Before I get into the nitty gritty of our application, I'm going to go over the current restrictions and guidelines which applications similar to this, as well as devices similar to this, already have on the market. So, according to the AHA, all training devices must include some sort of feedback system. And CPR devices available on the market today are typically very expensive, inaccurate, or just generally incomplete. So, based off of these things, we can see that CPR devices which contain ready and viable feedback during CPR, as well as accuracy and affordability, is needed on the market. A device which can be integrated into CPR training systems is already in place, such as mannequins, would be useful and effective in simplifying the CPR training process. That is where our device would come in. Our device would be able to um, include some sort of feedback system, as well as be accurate, inexpensive, as well as complete. On this slide, I will be getting deeper into our project and talking about the implementation. So, in order to implement our project, we worked with the bioengineering team in order to create a sensor for our application, which would work hand in hand to monitor CPR on test dummies and provide accurate user feedback. So here, if we look at the diagram, we can see that we have a test dummy with two accelerometers placed on the dummy. We then have our pressure sensor. As we perform CPR on the dummy, our sensor feeds output to our server. From our server, we pick up the data from our application, and our application provides the feedback to the user, telling the user the compression rate, compression depth, as well as notifying them of hands-off time. When we are within range, turns green. When we're out of range, turns red. For the user interface portion of this project, I'm going to be handing it over to Andy Lewis, who will be talking further and deeper about our user interface, how we implemented it, and what it displays and how it works.
Hi, my name is Andy Lewis, and I'm going to be talking about the UI portion for the Stayin Alive CPR training app. I was largely responsible for that part of the project. We used Visual Studio's Xamarin in order to implement the project, and we did that because it allows for cross-platform development. We can support iOS and Android with one code base. Based on conversations with our client and time constraints, we decided to focus on iOS. And with the UI portion in a Xamarin project, you have to use the tools of the platform. It does not cross-flow. The back-end code is the part that is the interchangeable portion. For iOS, that means using Storyboard Interface Builder and Xcode. And it is a great tool once you learn how to use it. It can be a bit of a trick at first, but once you get comfortable, the UI responds dynamically to different phone sizes within reason, and that within reason portion is devoted to the iPod Touch. I decided not to support that just based on the fact that it's such a small screen that I probably would have needed to develop a completely different storyboard in order to support it. And the iPod Touch probably isn't long for this world. It's either going to be updated to use one of the currently existing form factors, or it's going to be discontinued. I'm not sure why it's still around, to be honest, but it was going to be enough extra work, and I didn't think it'd be a good use of time, though it is indeed still possible. But otherwise, excluding the iPod Touch, managed to get everything on one screen with no scrolling. That was a goal. If someone's running a training session, I didn't want it to make it necessary for them to scroll around hunting for content and also keeping an eye on the students. So we're there. As you can see by these pictures, everything fits pretty neatly. And it does so across all the different iPhone sizes. If you look at it on a 12 mini, it's it's clear that we're at the limit for how much content we can fit on one screen before we need to implement a scrolling option. It's just we don't have room for more information without using some sort of alternative technique. But it looks to me as if we've accomplished this goal largely. If we look at the graphs over here on the right, I also implemented an option where as when time moves on and you accrue more data, the graphs will compress, fit inside that boundary, and at a certain point it becomes unusable. So within code, I implemented an option where if the time goes past 3 minutes, it will incrementally start to expand outward, and you'll need to scroll in order to see the rest of the data, but that allows you to have more useful graphs. That is the UI portion of the app. Thanks for listening. These two screens on the right here were the most challenging to implement, but in the end, you can see and use all of the buttons and data across all the available sizes in Apple's lineup. So I call that a success. Again, thank you for your time.
For the server and calculations portion of this project, I'll be picking it back up and explaining how we implemented the server as well as the calculations. The server portion of our project was necessary in order for our application to communicate with our sensor and vice versa. For this, we made use of MQTT. MQTT is a lightweight publish subscribe messaging protocol designed for low bandwidth, high latency, unreliable networks. So for our project, this was perfect. We made use of HiveMQ and set up an MQTT broker on their platform. Upon doing this, we set up the perfect environment for our two devices to communicate. Our sensor was able to send data to the server, and our application was able to pick up that data just as soon as it came. For the calculations portion of this project, we used the acceleration data from the accelerometers in order to calculate compression depth, compression rate, and hands-off time. In order to calculate compression depth from acceleration, we had to calculate displacement from acceleration. Compression depth was essentially the max displacement subtracted from, or the min displacement subtracted from the max displacement. Compression rate, we had to calculate the peaks and calculate the time between the zeros.
Hi, my name is Isaiah Haley, and I'll be talking about the network and data handling portion of this application. As this is a data-driven application, how we handle and control the flow of data is particularly important. In the real world, this application may be used in situations where multiple sessions of training are happening simultaneously. In order to allow for this, we structured the MQTT topics and network in such a way that allows for multiple sensors and multiple training sessions to easily be happening at the same time. The MQTT packets themselves contain the data in a JSON object that holds both acceleration and time values as transmitted by the sensor. As this data arrives, it is used to perform calculations where the depth of compression and the rate of compression are calculated. As our user interface is updated by the arrival of new data, we also must perform a smoothing operation where we average the compression rate and compression depth over the previous 3 to 5 seconds of the training session. We also do not receive all of the session data simultaneously, so we must perform interpolation operations on incoming data packets in order to fit the data in with the data that we have already received. After the training session, we perform some basic analysis of the session, such as calculating the average rate of compression, average depth of compression, and what percentage of time that the user spent within the target range for both rate and compression. This data is then made available for export and can be transferred outside of the application. Due to delays in receiving the hardware for the sensor portion of this application, we had to perform testing without the sensor. In order to get feedback on our application, I created a script that output sample data that was randomly generated to be within the bounds of expected incoming data. During the course of testing, many of the concerns that the users had revolved around the feedback given to the person being trained and the formatting and of the data being displayed to the user. One concern in particular was the data was being displayed and then changing too quickly and for the user to be able to read and make adjustments to their technique. In order to fix this, we implemented a system where the data being displayed is smoothed over the last 3 to 5 seconds of the training session. This lets the data change much more smoothly and allows for it to be read much easier by the user. We also updated formatting to bring all of the labels of the graphs into line with standards maintained by the American Heart Association.
Picking back up, I'm going to go over the timeline of our project. We began this project in September of 2020, beginning with the design. From October to the end of the semester, we were constantly working on getting out a proof of design. So, for our proof of design, we essentially had a working application that ran on our simulator with test data. Following last year into January 2021, the bioengineering team had made significant progress with their sensor, so we were able to begin testing with real data. From January to March, we were working on getting everything set up with the sensor, as well as making sure that the application was able to communicate with our sensor through the MQTT server. In March or in April, we were able to begin user testing, and now in May we are working on our technology handoff. Or at the time of this recording, that is completed. So that is our timeline.
While our app does give feedback to the user about their CPR technique, there are some features that uh, may be implemented in the future that will help increase the effectiveness of this app as a training tool. Um, those include a way to keep track of users over time. So that would be like a user login, record keeping, or a way to export the data directly to a database. Um, Another feature that may be implemented is some sort of sensor feedback where data is sent from the app back to the sensor in order to uh, display like a blinking light if the compression rate gets too slow, or display a different color if the compression depth is too shallow.
We would like to say a very special word of thanks to some people who were involved in this project. We would like to thank Dr. Edema for sponsoring this project and allowing us to work on it. We would also like to thank Professor Barchetta for supporting and guiding us through the project. This project was in collaboration with Kiera Flores, Gabriel Andriano, and Ana Meza Costa, and we'd like to thank them as well for working with us to create a viable product. Thank you.